All right. So, as Chris mentioned, we'll be presenting today about some fresh produce schooling applications, and honored to be able to speak here on behalf of our applications and happy to be a CODESYS system partner. So, first, we're going to little background on who we are. Myself, I grew up on a dairy farm in the Wisconsin area, as many did. And there, I eventually found my way into being a mechanic, keeping a lot of the facilities running, and was always trying to find ways to improve. Even as a in middle school, high school, I had this vision of a automated system that we could run the whole farm from a computer and everything took care of itself. And that eventually led me to stumble onto this thing called a PLC, and then I taught myself how to program those on some of the more common budget ones we have here in the US and found it was a nice way to get into programming with some high reward. Your code runs and motors turn on, everything goes. It's pretty cool. So I really enjoyed that. I wanted to learn more, which led me back to returning to school for electrical engineering with the goal of pursuing automation full time. In that process, I founded Bitmasked as a side business to help people in agriculture at the producer level. So the people actually growing the food itself, milking the cows, etc. And through some networking, that really took off, and here we are today. So personally, my CODESYS journey, we'll call it. When I first taught myself PLCs, I actually downloaded CODESYS, but not having a lot of coding experience or really knowing what I was doing, I was a bit lost and I never opened it again. And a few years later, I downloaded it again because I thought this seems like a very powerful suite, but still didn't quite have the skills to master it or maybe the drive. And then I started running into some shortcomings in some other environments we were using at the time where there were things I wanted to do that we just couldn't do. And I don't like being told no. So we pushed through figuring out this CODESYS thing, and I'm glad we did because now we've gotten to this point where we've realized any crazy idea we cook up, we can probably do it. It may take a lot of research. We may have to brush up on some of our German, but we'll get it done. So after seeing a lot of those results, certainly a firm believer in the CODESYS vision and really excited about the progress they're making. So Bitmasked, it's an interesting name it came up with. There's not a very unique story behind it other than I was sitting in a class about Bitmasked at the time, filling out the LLC paperwork, and I knew I didn't like spelling my last name over the phone. So I came up with Bitmasked, and of course, as soon as I spelt that over the phone for the first time, I realized I did not hit the mark on that bullet point. Um, our focus is being a system integrator for the agricultural industry with a focus even further at the producer level. So there's a lot of automation higher up the chain, the later processing of the products, but at the actual farmer level, we found there was a niche that needed to be filled. And it's a challenging one to fill because of, as you can see in some of my bullet points on the uniqueness, they're obviously everyone's cost conscious, but the numbers everyone is working with are a little bit different. When you're on the commodity production scale, your margins are in the single percents if you're lucky. And it's a very risk averse environment as well. If you take the grain farmers that we have, or even the fresh produce farmers we have, they only really get one chance per year to do the right thing. And in a lifetime, that's, 40 chances. You plant your crops in the spring, and any changes you try that year, if you fail, severely, it's very hard to recover from versus some of the other things where we're doing like continuous manufacturing of a product or something. They have a lot faster reaction time because they're not dealing with nature. Along with that, we see some low utilization rates on some of these things. A tractor, for example, on a grain farm in the Central Plains where all the corn is grown, may get 200 to 500 hours per year. Compare that with a mining excavator that's going to run nearly 8,000 hours per year. It's just a little bit harder to justify some of those ROIs. And your designs have to take that into account too, that these aren't 24/7. They're 24/7 when they need to run, but they aren't 24/7, 365 systems. I mentioned the value focus is definitely a thing as well, where we've really found success with the CODESYS platform, and many will point to the freemium model of CODESYS as being a success for that. But I'd argue it's our biggest savings are in development time with CODESYS. We can write our programs much faster and get farmers the value that they need and keep us in business as well, still making money. No existing PLC knowledge is something we run into on on the farm aspect as well, and that's a benefit to some extent. We don't generally go up against a hard spec of a brand X control system we need to use. So CodeSys has been very welcomed by all of our customers because they just want the best end results. And that also plays into the support side of it. So we tend to maintain remote access to a lot of these systems and that we support them directly ourselves. They don't usually have any on-site people that are helping troubleshoot or keep these systems running. It's generally us. My favorite part of this is the direct impact. So, as I mentioned, we work with producers and we also work with the OEMs that build some of this equipment to sell to producers and their dealers that distribute this. But across all of these customers, our systems have a very direct impact. So the one that usually signs the check at the end of the day is often the one operating this system. So when when you're working with them, it's a little more fun because it's really direct. It means if their ice machine doesn't break in the middle of the night, or it at least notifies them why it did break, they get to spend more time with their kids at home, and that's a little more rewarding. It also impacts our speed of development as well, in that we don't have much of a change process to go through to get things approved. That person sends us a text message, "Hey, I want this machine when it's going into harvest, this is happening, change this," and we do it. We log it in our systems, but there's not a lot of overhead to deal with there, which is nice. And as Chris mentioned, we're the newest CodeSys system partner, and our focus is ag projects here in North America. So next we're going to get into the need, and we could talk a lot about fresh produce cooling and agriculture in general, but to keep this as an interesting topic on point, we're going to do a very niche thing on broccoli cooling. And why broccoli? Well, broccoli holds a special place in my heart. Despite growing up on the dairy farm, my first paying customer was a broccoli producer in Virginia. And ever since then, I've found it very interesting. Maybe it's because I grew up with cows, so they're a little bit more boring to me, but this concept of cooling broccoli was very foreign to me and something I thought was very interesting. And it's relatable to everyday life. We should all be eating more broccoli than we already do. It's certainly a superfood. And the dairy farmer in me won't even judge you if you believe it just needs to be coated in cheese to eat, keeping two industries going there. So why do we need to cool broccoli in the first place? Where is this heat coming from? And what's unique about it? So broccoli, all produce has some sort of a respiration rate, but broccoli has a uniquely high respiration rate with a very dense um, structure. And what that respiration rate is basically that once the plant is cut, it's trying to sustain life by burning up all of its sugars. And through this, it's generating a lot of heat, and it's also consuming a lot of those nutrients inside of it um, to support this process. And we have a little chart here that kind of shows the respiration rates. If we cut at 80 degrees ambient temperature, or well, this is actually 80 degrees core temperature of the broccoli, but it follows ambient temperature with a little bit of a lag. In 1 hour's time, you can see we're going to self-heat about 15 degrees. So we're approaching 95, 100 degrees Fahrenheit in just 1 hour's time. That is a lot of energy. So we need to mitigate these two types of heat. And there's ways we can reduce the heat to begin with, but largely we need a bunch of mechanical refrigeration to remove all of this heat to preserve our crop. And so why is this heat an issue? If you go cut broccoli in your backyard and bring it in and eat it, it's fine. And that's true. But if you were to cut it and put it on your counter on, say, an 80-degree day and come back later on in that day, again, you probe that core, it's going to be in the 90s for temperature. And you may not notice it because generally you eat it right away. But if you leave it until the next day, you'll start to see these effects where the taste starts to change, the texture gets more rubbery, and something you can't see as easily is that the nutritional value is declining. And after just a couple of days on the counter, you're probably not going to want to eat it. And that's a logistical challenge for commercial production, of course, because we need a transit time from the field to the shed, to the distribution center, and ultimately to the grocer, and then onto the shelves. And while we try to keep that in a 24 to 48-hour period, there's still a lot of logistics at play there. So if we remove all of that heat fast enough, we can actually completely stop that respiration process and essentially put the broccoli to sleep and get a shelf life that can be as high as 18 to 21 days without a loss of any of our nutrients or flavor profile or our textures. And so here we have a little chart showing um, the time it takes for us to cool some broccoli with 2 tons of refrigeration. And none of this is fast enough. We need to cool broccoli down in that first hour rapidly. So there's two ways to manage the heat in the broccoli. One is harvest timing. And this is obviously out of our control as automation people. But if you harvest early in the day when the field is cooler, you're going to reduce what's called field heat. So if we start at a lower temperature, then we need less to cool it from there. And as you saw on that curve in the previous slides, it's not a linear curve on how much self-heating occurs. If we drop down to 60 degrees, we actually have a lot more time to work with that product. The other thing to note with this is cooling urgency. So this is a deal where if you were to just take your broccoli you cut in your backyard and put it in your refrigerator, you're not going to get the same effect because you cannot cool it fast enough. It takes these intensive processes we'll highlight later to really get that core temp down fast. And we do this through mechanical cooling, and there's various processes that do this, which we'll go over. The need for speed I mentioned on the last one. This is a chart showing this 7/8 time target everyone has for every kind of produce. And we have a chart here that we've borrowed from a research paper that shows a few processes and how the speed at which they can drop us down to our target temp of 32 degrees. Back to our home refrigerator example. The cooling's a very slow process in your refrigerator. The air is cool. It's also very dry. And so it's going to take several hours for it to cool your product down, and it may not outpace that respiration rate. So the damage is being done. The other issue is that the air in your refrigerator is very dry. That's also why you have that vegetable crisper drawer. It's not just for cheese, even though we use that in Wisconsin. You want to actually put your vegetables in there that helps with that dryness issue. And in a crop like broccoli, that's going to lead to dried out florets, and nobody likes that. So, um, one solution to this you think is let's dunk my broccoli in an ice bath, and that's actually what we do on a commercial scale. You could replicate what we're doing at home if you needed to, although again, it's probably more practical to just cut it the day you want to eat it. So with this chart, you can see here we're at 20 minutes. We're taking this product from 60 degrees, and in just under 30 minutes, we're already pretty close to our target temps. That's what we're looking to do. And as you see, higher hydrocooling is the quickest, slush icing is next, and forced air is going to be one of the slowest. Vacuum cooling is not on here, but we can highlight that process slightly here. So we'll go into this process. How do we actually do all of this? So on the industrial scale for broccoli cooling, we have several common processes. Historically, slush icing is one of the most common, and there are several reasons for that. Ice's advantages are that it has a stored cooling capacity, so we can put all that ice in that thing. We don't have to get that core temp down in our machine. We can get all of that ice into the box, and it can take the last 10 or so degrees out when it's in storage. It also has an accumulation of cooling capacity. And what I mean by this is if we're using another process like vacuum or forced air, we need all the tons of refrigeration present at that time to cool the broccoli. With ice, if we only harvest 8 hours a day, we can be building ice the other 16 hours of a day, and then we have a surge to use when the harvest comes in, and it balances out our refrigeration load. We can run these high horsepower compressors in off-peak billing periods and account for breakdowns. Many different minor operational advantages there. And then we also have the moisture retention factor. So items like when we do forced air or the vacuum cooling, we need to add moisture to prevent that drying effect, where with ice sitting in the box, we never have a moisture problem. Hydrocooling is another common factor, and this is well, a lot of iceless broccoli is done this way. This machine up here is a hydrocooling tube. So what we do with a hydrocooling process is just have tanks or plate chillers that cool the water with a lot of mechanical refrigeration near freezing to 32, 34 degrees, and we just pour it over top of it. And this has a big chain in it that moves through it, and the product will move through in 20, 30 minutes. Sometimes they're a batch system where you just set them in and cool them, but this is a continuous process style here. And a thing to note with hydrocooling as well is we'll actually combine that sometimes with slush icing to get the best of both worlds. And then another we have is down here. This is the hydrovac chamber. And what that is going to do for us is um, a much different process than anything else. So as we move this whole pallet of product over here, and this is actually lettuce where hydrovac is far more common, we'll move that into that chamber. We'll pull that vacuum way down to about zero point 0.5 millimeters of mercury. And at that, water boils off at about 40 degrees Fahrenheit or less. And so through evaporative cooling, we're able to cool that product. And then we use a big ammonia refrigeration system to condense all that moisture out of the vapor to speed up that process. It's quick enough. You can cool this entire load with cool ambient temps. So you can get this load down to its target temperature in about 25 minutes. The When we do this with broccoli, we do need to inject water in here to prevent the cooling thing, and then they call that hydrovacuum. And we've discussed forced air with the refrigerator. It's a little different when you do it on a commercial scale. You actually drape tarps over all the boxes of broccoli to force the air into them. And they use a process called humidified forced air, where they add some humidity to the air to prevent the drying. So ultimately, at the end of the day, customer demand is what drives ice versus iceless. There's a growing demand for iceless, but it is regional. East Coast, where we do a lot of work, there's still a lot of ice demand. We get into California, Southern California, where everybody has a vacuum tube already. There seems to be a lot of iceless demand, not a lot of iced anymore. So, get asked this a lot, and it was something interesting to me at the time when I first learned it. What's up with these boxes? How are we dumping ice into them and not having them fall apart? Well, they're wax coated. So that's how they hold up to all this moisture. And in some cases, we'll use plastic boxes. The unique thing about this harvesting process really is that this box on this pallet is the box someone carried through the field and cut the broccoli and put it in the box, or a machine carried it, but they cut it and put it into that box. And that box goes to the grocery store and never gets touched after it gets set on that pallet at the field. That's kind of an interesting step in this, and everything is built around less handling of those boxes. So, how do we even get this ice into the box? Well, the ice is produced, which we're going to go over in a future slide, and then it is shredded and blown into this machine you can see in the lower picture that is called a slush ice, clamshell, ice injector, multiple different names depending on who's selling it. And you can see these channels in the side of it, and these line up with the hand holes on the boxes. And so what's going to happen in here is when this closes around this whole pallet and the top lowers down, we're going to do an initial hydrocooling step that I mentioned earlier. And this tank below here is full of a nice ice bath from that shredded ice that was blown into it. We'll put that cold water over it to quick take out what we can for temperature, and then we're going to start up the agitator, which will force the slush ice down into the piping. It'll get blown up through these two hoses down the sides, and it'll flow through these holes. The water will drain out the bottom, and the cycle continues. And with the automation, we detect basically when we get up to the top, and we're really not putting ice in there anymore, and we've seen a certain amount of time elapse. We've determined the cycle's done. In some cases, we'll cheat the top up a little, flood the top with a little extra ice for transport, and then open the whole machine up and spit it out. Takes a couple minutes, and from there, they put it straight into the cooler to finish, to hold it at the low temp, and it'll go on to trucks and onto the grocery store. There's other methods to get the ice in the box at a smaller scale. This is the commercial style. At a small scale, it can be as little as just shoveling ice into the boxes. So, to give you a sense of scale, I mean, how much ice are we really talking about? I like this picture of the machine scooping out the ice. It gives a good sense of scale of what type of ice we're really producing. The producers we work with are generally using between 100 and 300,000 pounds of ice every day just to cool their broccoli. The machines that make this ice are obviously industrial scale, nothing like the hotel ice maker you see. And they do, an interesting part though, is that they really do operate on the same exact principle as the freezer in your refrigerator at home. They just freeze some water and then we harvest that ice, dump it out, start over. It's always a cyclic process. Um, There's several types of machines out there. There's tube machines, there's block ice, which historically, if you do a deep dive and nerd out on ice someday, you'll find how they used to make block ice with old ammonia chiller plants in the floor, and then they'd pop the blocks out. It's still common for some things. You find it for when they make your concrete, actually, for making buildings, and they need to shred ice for cooling it down. They'll use block ice because it stores easier. Plate ice is another common one, and flake ice too. We don't really work with flake ice, but it is out there. For all these ice processes, they need some sort of automation. Even back when these things were first made, they were all on relay timers and everything. Nobody's standing there flipping switches and really manually running an ice machine. So, I'll give you the secret recipe for ice. It's cold and water. And so the water part of that's easy. And then the recipe for cold is the refrigeration cycle. And this is the same for any refrigeration system really out there. There's some nuances to them all, but essentially we're using a compressor to take mechanical energy and compress a low pressure gas into a high pressure gas, which is going to end up going over here to our condenser, which will, as the name implies, condense that gas into a liquid and reject the heat into the atmosphere. And then it will continue on to our evaporator, where we're actually building the ice, and that is going to absorb the heat from the water through boiling off the refrigerant, which then returns to the compressor, and the whole cycle keeps repeating. We generally work with ammonia systems, as that's common for these large scale ice plants. And they run a slightly different for those that are familiar at least with automotive and home air conditionings, we run flooded evaporators instead of direct expansion. So we have that whole evaporator full of liquid ammonia, either through a surge tank system or a recirculating system. And that ensures a nice, good direct contact with those plates for a little more efficiency. And ammonia itself, the latent heat capacity is unreal. Uh, it's a very popular refrigerant. It lost some popularity, but it is making a comeback with the push towards natural refrigerants because it's one of three natural refrigerants, the other two being propane and CO2. Oh, I had a note here as a sense of scale again for that mechanical energy. A 300,000 pound ice plant is going to have roughly two 150 horsepower compressors. So the tube ice process, there is a pretty picture of a nice tube ice chunk. These machines are built like any other shell and tube heat exchanger. It's an array of approximately 1 inch diameter tubes. They vary. And the water is distributed down the inside wall of that tube in a thin film, and the refrigerant's on the outside tube. And the ice just simply builds from the outside in on this type of machine. There's others that build the outside out. Same process. It progressively builds in thickness, and with this process, of course, each layer of ice builds slower and slower and slower, and the diameter is smaller and smaller and smaller. So we're getting less ice per time. So we need to maximize that, and that's where that hole comes in. When we're looking at that hole, we want to be at a size that gets us the most tons of ice per hour when we're doing fresh produce. If you're doing bagged ice that needs to go to the store, you need to get 20 pounds of ice in that bag. And then you may need a little bit tighter hold just for volume reasons. But for produce, we want maximum ice. And what we found on the inch and an eighth tube machines is that's about the size of a pencil. There's also always a risk too, if we start to get this hole too tight, we can freeze the machine up. And that is where these tubes will not drop. And that will stop production for quite a while. In the worst case, you can even burst a tube. Uh, so to continue on this, that is how the ice is built. So it's a continuous process. We freeze the water, which builds the ice up in those tubes, and then the way that we get the ice out of there is with a thing called a hot gas defrost. So in that process, we're always putting the cold liquid into these tubes to freeze the water, and then we flip the machine into what we call a harvest. And at that point, we inject the hot gas from the refrigeration cycle right into the machine. It warms the tubes up, and all those tubes fall. And when they're falling, there is a cutter on the bottom that is spinning, and it's sizing them into these little inch and a half or inch and a half long pieces. And that harvest process will take about 2 minutes, and then we'll return back to a freezing cycle. And we have a lot of little steps in between there to balance some things out, but that's the gist of it. So we have an example here of a plate ice machine. Despite me talking about tube ices the whole time, this is a recent plate machine we did with CODESYS. And this kind of gives a nice visual overview. And in this scenario, it was a turbo machine with 6 sets of plates that build plate ice. It's the same process as building tube. It's just the water goes down the side of the plate, the refrigerant's on the inside, and when we go into that defrost, instead of a cutter, the plates just fall and shatter. But as you see here, we're defrosting 2 sections at a time, and this is important for balancing our compressor load. We always want to have a certain amount of load so we can maintain that head pressure to have that hot gas for a defrost. We have some scenarios where we run individual machines and we need to add a false load just to keep those pressures up so we can get that ice out. All right, execution with a repeat photo. So this is a cyclic process, and we're going to run through those steps that we discussed a little bit earlier, where we're freezing our um, our water first. So we need to set a bunch of valves, and we need to make sure we have the right motors running. Well, for freezing, all we need is the compressors running. That's not a big deal. And then we have a timing sequence. And so this is where the benefits of CODESYS really start to show up. In the past, we ran on some fixed timing schedules the operators would set up, and and it was pretty rigid because the environments we were using were did not allow us a lot of customizability in our algorithms, and it just got very convoluted. And not being able to use the structured text when we really get into some of that was tough. And with CodeSys, we're able to do that, and we even have the flexibility to go outside a traditional IEC environment using shared memory on the Linux controllers we use to have something else do this predictability for us on what our freeze cycle needs to be. For now, we keep it simple, but that knowing that option is always there is a very nice benefit. So, what type of dynamics, freeze cycles are we trying to do? Well, when you build an ice manufacturing plant, you put these machines inside a cooler. So your temperature is always constant, and then your freeze time is always constant. When we do them on farms, they generally just have them sitting outside. And ambient temperature, the sunlight, everything can swing our freeze times from 8 minutes to 15. So we're always looking at a bunch of key factors, how much water we're using, what the ambient temperature is, did we see the ice drop and for how long? And we can use those to kind of adjust our set points so we're maximizing our ice production and at the very least, at least preventing issues that could creep up. There's some business realities, of course, about some of these programs. So we have a seasonal use that I mentioned earlier on these machines. I have a woodpecker outside. And that can make things very difficult to get the ROI on. They tend to run about 2 to 6 months. And then they sit for a while. So then startups can be challenging. So it's nice that we have a lot of monitoring in there to really help guide these customers on how to debug these machines. And then also keeping the user interface kind of intuitive because when you step away from something for 6 to 8 months, you completely forget how to use it. And that's why you will see a little more color in some of our designs than may be recommended sometimes. Uh, and then with this usage, we're often retrofitting older equipment. They buy used machines, bring them in, and we retrofit them to all work together. And at the end of this, through this execution process, we've found using CodeSys to develop these, we have a lot better, faster development time, more reliable code, and a better ROI for the consumer, for the end user. All right. And then we have some basic principles that we follow in our code design. And those revolve around following a practical object-oriented approach. So not as strict as some may be on it, but we like to take some of the key components out of that object-oriented design approach and use them where fit. So we're not trying to check a box and fit into any camp A or camp B on anything. We just want to what can give us the most reliable, readable code with a quick development time. And a big one of that has been not repeating ourselves. So anything, we tend to write everything once and re-instantiate that as much as needed. And that's made possible through a modular design with breaking everything down into small components. You can see we reuse things like our analog limits will all be reused in an analog block, and we just keep stacking features in as needed. We'll use some other features like the inheritance that CodeSys allows you to do, so we can have a base functionality and bring that up to our next one, next level function block. In other cases, we'll do it through more of a composition approach if that's more applicable. And Something we borrowed kind of from the software world as well is minimizing the globals. I know traditionally in PLCs we make everything global, and that can be nice and can make it very easy to just start manipulating variables everywhere, but it can lead to some spaghetti that's very hard to debug. So we keep things local and interact with our function blocks through their interfaces with the methods and properties that they inherit. And the other thing we found with this is we're big believers, of course, in testing code, and everyone says they are, and we're not perfect either. But having this interface means when we go to simulate stuff, we're not spending any time setting it up. It's just ready to go. That's something found very frustrating in some other environments was the setup involved separate software for simulation, separate, you had to delete a bunch of stuff, you had to add a whole bunch of extra things here and there that just didn't work. And with CodeSys, you click a button and you're simulating. Another big principle, everyone says they want readable code. That's a given, but the execution of that varies. And I came across enumerations in CodeSys quite early when I started using it and have never really looked back from that. I think when it comes to state machines, using the power of a case statement with an enumeration is one of the most readable things you can write instead of using magic numbers and leaving gaps in them just in case down the road you want to add something. With this approach, we never have that. Now, we can't do those things where you just add +1 to the step, but I think that overall this really improves the readability and incrementing your steps with math is hard to troubleshoot anyways. It does involve a little more typing. It makes things a little bit longer, but when we come back into this, we know what's going on. And as you can see, there are very few comments in here. It's fairly written out of what it is. Um, I once heard a phrase that said comments are mostly bad, and your initial reaction to that is, oh, this is a crazy idea. But then when you think about it, it has some merit that, if we're commenting something because we wrote a non-descriptive variable name, why don't we just write the descriptive variable name? So kind of follow that concept, and then we comment the intent of the code where we need to, or why we're doing something. Because another big thing we've ran into with comments too is that they're not maintainable in a way. You have to manually go back and update them. They don't refactor with everything else. And then we have our visualization. So this uh, is an interesting story. When I first started with CodeSys, I was unsure what to make of the visualization. It seemed a little bare when on first install. Um, But after using it for quite a while, we realized how powerful this is, and it's one of the big selling points of staying in CodeSys, is that all of our visualizations are tightly coupled to our logic. It's all one environment. There's no worries about handoffs. Everything's there. So we follow this approach where if we write a function block, it gets a visualization written for it as well, because there's always something we need to work with in there. And then each visualization that gets written has an instance of that function block. And that makes things very easy to work with. We can map anything to it. It speeds up our development time. Any code we have for that visualization, like this ISA analog indicator block over here, there's a lot of code to scale all of these different rectangles to be what they need to be, move this pointer where it needs to be. All of that resides in its own method within that. So within our, say, analog input block that we have a method that's running all this visualization specific code. And that's actually called directly from this visualization only when when it's rendered on the screen. So it kind of improves our efficiency a little bit. Another very powerful thing about CodeSys, a few people have mentioned in their talks, is the frames. And we love that with this analog indicator block, for example. We built this, everything is normalized to 100 pixel height because it's super easy math. And then when we instantiate that into a frame, we can make it 500 pixels. It doesn't matter. It automatically does it all for us. We don't have to change anything in our code. We can develop to a standard point. Along with that, you can use your frame switch variables. So in the past, you would have a block with a whole bunch of visibility variables, turning things on and off. Maybe we don't want the operator to have a start stop button for this motor. So we're going to hide those unless they're logged in or they have this permission or they're in this operating mode. Instead, we'll just build two separate uh, visualizations with each what we want to see and just change that switch index. And from there, we use our frames as our parent generally. Like if we have a motor that's in its frame, as you saw back on the example we had, and then you can click into that to progressively bring up more information. So this ISA bar is a great one. This bar is what's displayed on the screen. You click into that, it brings up another dialog that's not actually shown here. And then from there, you can go into further things where you can adjust your scaling, change a bunch of configurations here, and change your limit values, configure them how you want. Uh, Or even, I'm incredibly lazy, so this destination pump pressure high is not typed in. That is dynamically generated from what we call that variable. That's kind of a neat thing we found we were able to do with CODESYS. And that does rely on giving it a useful name to begin with, but and as you can see, it could use some work to remove the brackets, but overall that has really sped up our development. I like giving people a lot of information on the HMI, not only what is this thing called in the schematics, but a more plain English thing of what am I actually looking at here. And that comes from being a farmer myself. We didn't always quite understand the schematic in real time. It's nice to just have some plain English. And this kind of comes back to our last principle here that everything should be in the visu. This has always been something I've strived for because this goes back to not having PLC support on staff at most of these facilities. So if no one's going to be able to get in and adjust the code, which we don't like to design with that in mind anyways, but since it's not feasible, we have to design with that in mind. And we put all of our configuration in the visualization. So you see here, all of the scaling for this sensor is in here. We don't do it in the code. It's adjustable by the user. They can go through and invert a sensor if they need to. If they put in a normally open versus normally closed, they can um, they can move it to a new I/O point. They can rename it to whatever they want to call it. This alternate description here for a limit is one of those. If this limit is controlling a pump cut-in value, they can just type that in so that it's a little more obvious to them. We try to put everything we can in there, and one of the really cool things we found specifically for our OEM customers is that we found a way with CodeSys you can um, change your Ethernet settings for your Ethernet adapter within your application. You can change all the IP settings from the Visu in runtime without stopping the processor. Now, you have to blip the port, or at least the way we did it, you had to disable the port for one scan, but you can change your IP addresses and everything while you're running and even change the protocols, which is very useful. We can ship this standard piece of equipment out where this Ethernet port that's on adapter that's on our controller. This is your plant one that you guys can configure to use. Maybe you want Ethernet IP or you want Modbus TCP, and we don't know what you want for your IP settings. You choose your protocol, you choose your settings all through the visualization. Nobody has to get online to try and change any of this stuff. It's been a very powerful tool. And of course, yeah, no waste of time with copy, paste, find, replace. That's kind of a principle of this whole concept. So to wrap this presentation up, we started talking about broccoli, which was my first customer and uh, one of my favorite topics to talk about because it's pretty impressive what goes into actually getting broccoli to the store. So, and behind that freshness that we deliver to the store, we've got all of our heat removal. that occurs through our refrigeration processes that we automate with CODESYS. And really, in the end, it all comes down to kind of control, understanding the process deeply enough to make it smarter. That's one of the reasons I gave this presentation is that we've gone down the path of really trying to understand the refrigeration process, the physiological cycle of this crop, and how can we try to improve this process for these growers versus just being someone else that knows how to replace some relays and timers and put them into a PLC. We've learned the just because the procedure the OEM of the ice machine put in the manual 30 years ago, well, that's what they had at that time. That's not necessarily what's going to give us the best end result. And and we focus on taking our experience, especially in the ag world, some good engineering principles we've come across along the way, and the modern tools like CodeSys, and turning them into some automation that's reliable, efficient, and repeatable. So we do some smaller machines once in a while, or these big 300,000 pound ice plants that are quite fun. The goal is really the same. We got to keep the product cold, keep our process simple for the end user to understand, and keep everybody really happy and running good. So at the end of the day, our automation is not only making ice, it's definitely keeping the broccoli nice, crisp, long shelf life, and hopefully keeping some operators smiling. So with that, I have some contact info here. LinkedIn is certainly the best spot to keep up on any of our projects. Our website is updated occasionally as well. And if you peruse the LinkedIn, you can find some videos of these ice machines actually making ice. It's pretty impressive to watch them drop about 1,000 pounds of ice at a time. And if you're looking for broccoli, find some at your local grocery. Go buy some tonight. And thank you very much.